Hi Chem students, welcome to a tutorial over the electromagnetic spectrum and wave calculations. Please have out your chemistry notes and a calculator. Most, if not all of us, have seen fireworks on the 4th of July and neon signs brightening the city streets. But how is light emitted? And why do different chemicals give off different colors? To answer these questions, we must study electron movement within the electron cloud and understand the properties of light. An interesting property of light is that it can behave as either waves or particles, depending on the circumstances. This is called the wave-particle duality of light. The fact that light can act as particles and can transfer all of its energy to another particle, such as an electron, was an important fact in the development of the quantum mechanical model or modern atomic theory. In this unit, we will focus on the wave nature of light. Waves have three primary characteristics: wavelength, frequency, and speed. One wavelength is the distance between two consecutive crests or troughs and is shown in the diagram. Wavelength is represented by the Greek letter lambda. Light is composed of many waves of many different wavelengths, ranging from large waves that are kilometers in length to small waves picometers in length. When describing a wave, we usually use meters. Frequency is the number of wave cycles, successive crests or troughs, that pass a given point per unit of time. It is measured in cycles per second or hertz. The symbol for frequency is the letter F. In the diagram below, the top wave has a high frequency and the bottom wave has a low frequency. The last characteristic of light is speed. All forms of light travel at the same speed in a vacuum. This is the most accurately known constant in the world. The speed of light, which is 3 times 10 to the 8th meters per second, is represented by a lowercase c. Although we often think of light as the energy that enables us to see, visible light is a very small portion of what is called the electromagnetic spectrum. The electromagnetic, or EM spectrum, includes all the characteristic wavelengths of electromagnetic radiation that are emitted by an object, molecule, or atom. You've probably heard of most of these types of electromagnetic radiation. Radio waves carry the songs and information we listen to on the radio. The number of the radio station, for example 95.7, refer to the frequency of the wave. Microwaves are used to heat food and drinks. Infrared radiation is emitted by heat lamps to help keep reptiles and other animals warm and by your TV remote control. Certain types of thermal imaging devices capture infrared radiation emitted by objects so you can see them at night. Our eyes detect light in the visible light range. We see colors when certain wavelengths are reflected off of an object. If all the colors are reflected, the object appears to be white. If all the colors are absorbed, the object appears to be black. Visible light includes the colors of the rainbow, and the wavelengths range from approximately 700 nanometers to 400 nanometers. Red light, which has the longest wavelength, is just after infrared radiation. Violet light, which has the shortest wavelength in the visible range, is just before ultraviolet light. Ultraviolet light is used in tanning beds, and forensic scientists use it to detect blood and other bodily fluids at a crime scene. X-rays are used to detect broken bones. And lastly, gamma rays are emitted during nuclear reactions. To remember the order of the EM spectrum, from longest to shortest wavelength, use the saying, "Riding much in bands uses extra gas." Frequency is determined by the wavelength of a wave. Watch the wavelengths as they leave the screen. This illustrates an important property of light. The shorter the wavelength, the higher the frequency. Wavelength and frequency are inversely related, which means as one increases, the other decreases. The speed of light, wavelength, and frequency are related by this formula. C equals lambda times F. This means the speed of light equals the wavelength times its frequency. Here's an example problem using that formula. It says, what is the frequency of radiation with a wavelength of 3.82 times 10 to the negative 7 meters? What part of the electromagnetic spectrum does this fall? The first thing you need to do is rearrange your equation to solve for F. So to do that, you just divide both sides by lambda. So we get F equals C divided by lambda. Then we can just simply plug in our numbers from the example problem. So knowing that the speed of light, which is c, it goes on top. 3.00 times 10 to the 8th meters per second divided by the wavelength that they gave us, 3.82 times 10 to the negative 7th meters. After putting this in your calculator, you get 7.85 times 10 to the 14th hertz. When you look this up on the electromagnetic spectrum, you can see this falls in the visible light range. Not all properties of light can be explained by the wave model. Max Planck, the bottom left, and Albert Einstein, the bottom right, refined our understanding of light to include its particle nature. Light can be described as a stream of particles called photons. The details of the particle nature of light will not be investigated in this class. We will only highlight the relationship between energy of light and its frequency. Light also has energy. When light acts as a particle, it can transfer all of its energy to another particle, such as an electron. Energy and frequency are directly proportional. This means as frequency increases, energy also increases. Therefore, long wavelengths, which have a low frequency, also have a low amount of energy. The low energy end of the spectrum includes radio waves, microwaves, and infrared radiation. Electromagnetic radiation with short wavelengths have high frequencies and have higher amount of energy, which is why they can cause significant damage to our skin and DNA. The high energy end of the AM spectrum includes UV light, X-rays, and gamma rays. The energy of a photon and frequency are related by this formula. Energy equals H times F. This means that the energy of a photon equals Planck's constant, which will always be given to you, times frequency. Let's look at an example problem. How much energy does a photon of light with frequency of 4.2 times 10 to the 8th hertz have? What part of the electromagnetic spectrum does this fall? Well, for this equation, we can just plug it directly in. Energy is going to equal H. So H is Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. I'm going to give you that constant, so do not worry about memorizing it. We're going to multiply this by the frequency, which they gave me in the problem, which is 4.2 times 10 to the 8th hertz. After putting this in my calculator, I get 2.8 times 10 to the 25th joules. When looking this up, by looking at the frequency on the electromagnetic spectrum, I can see that this falls in the radio wave section. I hope you enjoyed this tutorial today and it helps you to understand the electromagnetic spectrum. For more help, please seek our website and the completed notes key online. Have a great night.